Today, we're going to practice a little bit more with graphing rational functions. This is a really big part of this unit. It is something that you'll be expected to be very good at when you're in calculus next year. So we really want to make the time to perfect this. So today, all we're going to do is more examples of that process that we started yesterday. Remember, the first step was to find our y-intercept. The second step was to find any x-intercepts. The third step is to see if there's any removable discontinuities, which we will have to remember for later on. Fourth step is to find any vertical and horizontal asymptotes. Fifth step is to make a chart, x and y. And sixth step is to make the graph and then double check to see if there's any holes in your graph, which are the removable discontinuities that you would have found on the third step. Okay, so let's take a look at our first example. F of x equals 3x over x minus 2. Again, the first thing that you're going to be doing in each one of these problems is trying to find any y-intercepts, and that involves plugging a 0 into your formula everywhere as the x value. So in this particular problem, you're going to get 0 over negative 2, which is 0. So my graph is crossing the y-axis at 0. In other words, I'm passing through the origin. Okay, x-intercepts. X-intercepts are found by setting your numerator equal to 0. And if you divide both sides by 3, you find out that x equals 0. So I'm crossing the x and y-axis at the exact same place, which is the origin. Okay, third step. Are there any removable discontinuities? That's the next thing we want to look for. Well, the top part of this fraction and the bottom part of this fraction don't have anything that reduce, so this problem is not going to have any removable discontinuities, so there are no holes in this graph for us to worry about. Vertical asymptotes. Vertical asymptotes are found by setting your denominator equal to 0, and if you set the denominator equal to 0, you're going to find out that x equals 2 is a vertical asymptote for your problem. So if I go to where x equals 2 and I draw in a vertical dotted line, don't forget to label it, x equals 2. All right, horizontal asymptotes. Who's got the bigger powers of x? As we look at this formula, we see that the bigger powers of x they're actually the same on both the top and the bottom. So you make a ratio out of the leading coefficients, 3 to 1. Y equals 3 is my horizontal asymptote. And go ahead and draw that right away on your graph. And label it. Okay. All right, next. So that was steps 1, 2, 3, 4, 5. All right, 5. We want to make a chart. And in this chart, we want to pick some x values that are from both sides of our vertical asymptote. So our vertical asymptote is at 2. So I would want to pick some numbers that are smaller than 2, like 1 and maybe negative 1. And if you're wondering why am I not picking an x value of 0, well, we already know at an x value of 0 that our y-intercept was 0. So we actually already have that point on our graph. So what I'm going to do now is I'm going to plug these numbers into my equation to find out the y's that go with them. If I put a negative 3 in as my x value, I'm going to have negative 3 over negative 1 minus 2, which is negative 3, which means my y value at negative 1 is going to be positive 1. And if I put in an x value of 1, we're going to get 3 over 1 minus 2, which is negative 1, which is negative 3. Okay, so from the 3 points that I have plotted on the left-hand side of the vertical asymptote, at 1, negative 3, 0, 0, and 1, negative 1, 1, I can see that the graph is probably doing something like this. It has to bend so that it can get close to both my horizontal asymptote of y equals 3 and my vertical asymptote of x equals 2. Now, I've got to pick some numbers on the right side of 2 to figure out what that side of the graph is doing. So I'll pick x values of 3 and 4 and plug these numbers into my formula. For an x value of 3, we're going to get 3 times 3, which is 9, divided by 3 minus 2, which is 9 divided by 1, which is 9. So, oh my gosh, I don't think my graph goes that high. 1, 2, 3, 4, 6, 7, 8, 9. So at 3, my graph is way up here. And if I put an x value of 4 in there, we're going to get 12 for the numerator divided by 4 minus 2, which is 2. 12 divided by 2 is 6. So at an x value of 4, 3, 4, 5, 6, right here about. Okay, so again, I've got 2 points on the right side of my vertical asymptote. It looks like it's going up and then approaching my horizontal asymptote from above. So again, make sure that you're putting a label on this. You want to put the full original equation somewhere on the picture. F of x equals 3x over x minus 2. And I have already labeled my x and y axis, so this is now a complete problem. There were no removable discontinuities, so I don't have to go back on my graph and make any holes. All right, let's take a look at example number 2. The numerator for example number 2 has already been factored for us. Eventually, we're probably going to want to factor the denominator, but for right now, let's talk about finding any y-intercepts. So y-intercepts are found by putting a 0 into the formula everywhere for x. So 2 times 0 minus 1 makes negative 1. 0 minus 2 makes negative 2. So my numerator would be negative 1 times negative 2, which is 2. And the bottom part, when I put a 0 in everywhere for x, is 0. So you have 2 over 0, which is undefined. Again, what that means, if you have a y-intercept that's undefined, is that your graph never actually touches the y-axis. Probably means my y-axis is a vertical asymptote. X-intercepts. X-intercepts are found by setting your numerator equal to 0. So basically your 2x minus 1 and your x minus 2 are equal to 0. So that's giving us answers at x equals 1/2 and x equals 2. I feel like we've done this one already. And the next thing we're going to do is we're going to look for removable discontinuities. Again, with removable discontinuities, you better factor that denominator and see if there's any reducing that happens. There is. So my removable discontinuity is that x equals 2. So it's not really going to be an x-intercept. It's just going to be a hole in the graph. Now we're going to look at vertical asymptotes. Anything that's left that doesn't make your denominator go to 0 is x equals 0. So that means your y-axis is going to be your vertical asymptote. And then horizontal asymptote. We're looking at the degree on top, which is a quadratic. The degree on bottom is a quadratic. And the leading coefficient of that quadratic on top would be 2 in front of the x squared over 1 in front of the x squared from the denominator. So this is going to be y equals 2. I think this is actually the graph that we made in our previous day's notes. Doesn't hurt to do it again. All right, so because my vertical asymptote was at x equals 0, I'm going to want to pick x values from both sides of my vertical asymptote. So maybe I'll pick -1 and -2 and +1. And I can't pick 2 because that's a removable discontinuity, so I'll pick +3. If I plug these numbers into my formula to find the y's that go with them, for my -2 value, -2 times 2 is 4, minus 1 more gives me 5. So this reduces to just be 2x minus 1 over x. So we have -5 over -2, which is 2.5. When I put in the -1 as my x value, we're going to get -3 over -1, which is 3. So this side of the graph is going to be here and here. So this is what this side of the graph is looking like. And down here at an x value of 1, we're going to get 1 over 1, which is 1. And at 3, you're going to get 5 over 3, which is 1.5. 6 repeating. So at x equals 1, you're getting 1. At x equals 3, you're getting 1.6 repeating. We also had an x-intercept of 1/2, so that's where we're crossing the x-axis right there. And so I'm going to try to draw on my graph that passes through these points and bends to get close to my vertical asymptotes. We've got to label the equation with the original equation, which was 2x minus 1 times x minus 2, all getting divided by x squared minus 2x. And one last thing, we always check for removable discontinuities. We do have a removable discontinuity, so wherever my graph was at x equals 2, erase it and show me that there's a hole there. Yeah, this is the graph that we did before. So make sure everything's labeled. All right, last one today is going to be example 3. And example 3 is showing us a function f of x, where we have 2x squared minus 18, all getting divided by x squared minus 4. Again, we always start with y-intercepts first. So if I put a 0 in everywhere for x, you're going to get negative 18 over negative 4, which is going to be 4.5 on my y-axis. 1, 2, 3, 4, 5. So right there. Okay. X-intercepts, if there are any, is going to be found by taking your numerator and setting it equal to 0. So I'm going to divide everything in this problem by 2 on both the left and the right. So that gives me x squared minus 9 equals 0. And this is going to give me answers of 3 and negative 3. So we think that both of those are going to be solutions. So I think I'm crossing the x-axis at negative 3. And I think I'm crossing my x-axis at positive 3 as well. Okay. Next step, removable discontinuities. Let's see if we have any. We've already factored the top. It was 2 times x plus 3 times x minus 3. And now I'm going to factor the bottom. X squared minus 4 is going to give us factors of x minus 2, x plus 2. So in this problem, there are no factors that cancel out. Because there's no cancellation between factors from my numerator and denominator, that means I will not have any removable discontinuities. So no holes in our graph for us to worry about, which is kind of nice. Vertical asymptotes are going to be found by setting my denominator equal to 0. And I've already got my denominator factored up here, so that's going to give us answers of x equals 2 and x equals negative 2. You could just write it like this, x equals plus or minus 2. And what that means is I'm going to have a vertical dotted line here. At x equals 2. And another vertical dotted line here at x equals negative 2. So the horizontal asymptotes, the last kind of asymptote for us to look for, when we see what we have in terms of degree, we notice we have the same degree on top and bottom. They both have x squareds, and the ratio of the leading coefficients is 2 to 1. So my horizontal asymptote is going to be y equals 2. So I need to put in a horizontal dotted line, just like I did with the vertical dotted lines, and label them. Y equals 2. Okay. So at this point, we're going to make an XY chart. Now, the fact that we have 2 vertical asymptotes in this problem makes this problem a little bit more challenging. The reason why it's more challenging is I have to pick some numbers that are going to be on the left of negative 2. I already have negative 3 as an x-intercept, so you might want to also pick negative 4. I'm going to have to pick some numbers in the middle, in between the 2 vertical asymptotes. So maybe negative 1 and positive 1 would help me figure out what's going on in the middle. And then I've got to pick some numbers out here to the right. I already have positive 3 as an x-intercept. Maybe I should pick positive 4 to see what's going on out there. Okay, so again, we're plugging our values back into the formula. There is no reducing of this formula, so this means I'm going to have to do some heavy-duty math. Negative 4 squared is 16 times 2 is 32. 32 minus 18 is going to be 14 for my numerator. And negative 4 squared is 16. 16 minus 4 is 12. So I get 14 over 12, which is 7/6. That's about 1.16 repeating. Okay, so when x is 4, I get a little bit above 1. When x is negative 1, we're going to get negative 1 squared, which is 1, times 2 minus 18 gives me negative 16. And the bottom part of the fraction is going to be negative 1 squared, which is 1, minus 4 gives me negative 3. This is going to be 5.3 repeating at here. So 5.3 repeating is about here. Okay, when I put a positive 1 into this formula, you're going to see that it ends up being the same thing as negative 1 was, because when you square 1, it's the same as squaring negative 1. So you're going to get negative 16 over negative 3, which again is 5.3 repeating, about here. And when you put positive 4 into the formula, you're going to find out you get the same answer as when you put negative 4 into the formula. You're going to get 14 over 12, which is about 7/6, which is about 1.16 repeating. So what we're actually finding out about this graph, and hopefully you'll remember the meaning of this, it is actually going to be symmetric over the y-axis. That means this is an even function, believe it or not. The left side of the graph has to get close to the horizontal asymptote and close to the vertical asymptote, so it's going to look like that. The right side of the graph is doing the same, kind of the mirror image of what we're seeing on the left. And the middle part of the graph, well, it kind of looks like a U that's pointing up, but the ends are trapped. It's not a parabola. We can't say it's a parabola because it literally is going to be going almost straight up and down because it's trapped in between two vertical asymptotes. So again, make sure that you're labeling somewhere on your graph the full equation that created this. And also make sure that you've labeled your x and y axes. And that's it. This is how you create. Oh, by the way, there were no removable discontinuities. So that means we don't have to go back and put any holes in this graph. And this is how you make the graph of a rational function by hand. Okay, try the homework problems that I've given you for tonight.